So let's summarize. So far, we've looked at projection signatures as one mechanism by which we are able to take a binary region and summarize it in some way, or, well, represent the binary region. And the two ways we looked at were, first of all, to encode the boundary of the binary region as a sort of signal. And so that's an example of a type of signature. So we would refer to boundary signatures. These are quite well used. They're quite widely used in characterizing shapes, particularly of biological structures or structures in the natural world. So doing that has been used to classify different types of leaves, different types of fish, and so on. And some of these things are actually in use in databases. So you can retrieve objects which have certain boundary signatures. But I also, in discussing this, we talked about, for example, the process of finding the center of a region. And so there is a technique known as image moments, and in particular when applied to binary images, we would call them binary image moments, which provide a very elegant way of describing a region of an image represented as just a collection of white pixels on the dark background with a number of values. In fact, you've got a very large number of possible values that you could use, and you effectively compute the moments up to different orders so collections of moment orders can be used to describe binary shapes or binary regions in quite an intuitive way. And although these techniques are not widely used in the computer vision research field, they are practically extremely useful, and they're very powerful measures. So we're going to start with the definition first of all, of simply binary moments. And we will see that this is quite related to the technique of statistical moments, or moments of statistical distributions, which are sort of understood in the theory of statistics. But they're also related to topics in mechanical engineering, where we sometimes want to compute the center of mass of a two-dimensional shape or a three-dimensional structure. So the definition of binary moments has associated with it the concept of an order. So generally speaking, for two-dimensional binary moments, you talk about an order which is given as the sum of p plus q, where p and q are defined like this. So the binary image moment, well, in fact, the image moment of order pq, of order p plus q, actually, as you'll see, there are different values of p and q that give the same order. So, or rather, if I talk about order 1 binary moments, there are two values, or there are two different moments associated with the first order. So the first, let's look at the definition. So the definition is like this: MPQ is the sum of m to the power of pn to the q, fmn. So just to remind you, fmn for a binary image region is going to take values of 0 or 1. So it's very simple for a binary image. You can also extend this definition of moments to incorporate grayscale regions. So this definition is also consistent with working on grayscale images. But when it becomes binary images, it kind of becomes quite trivial. Each non-zero pixel value, therefore, taking a value of 1 rather than a value of 0, what you're doing is you're taking that pixel value of 1 and simply multiplying it by its row coordinate raised to the order of p, and its column coordinate raised to the order of q. So the calculation is actually pretty simple. And that gives you, so if we take, for example, the first order binary image moments, there will be 2 of those, and those will be the values of P and Q such that P plus Q is equal to 1. So first order, P plus Q should be 1, and there's two cases that we can have that satisfy that. Either P is 1 and Q is 0, or P is 0 and Q is 1. And so therefore we have 2 first order moments. So both of these are first order moments. M10 and M01. And so M10 is simply going to be equal to this expression. So that's just plugging in P is equal to 1, Q is equal to 0 into this expression. And M01 is simply going to be this, which is just plugging in P is equal to 0, Q is equal to 1, again in this expression. Okay, so you've got this general expression, and for certain P and Q, you simply simplify this. So here, all we're doing is we're taking within an image all the pixels that have a value of 1 and just adding up their row coordinates. And here, we're taking all the pixels that have a value of 1 and adding up their column coordinates. It's as simple as that. So those are the first order moments, and there are 2 of them. There is also a 0th order moment, which is simply given by P is equal to 0, Q is equal to 0. And so all you do is you end up adding up the number of ones within the region. Now, note that if you you can apply this calculation, and in fact these calculations over here, to any image that's a binary image. So for example, if we think back to our rice grain image, remember that we had when we did connected components labeling, we created we had a Boolean operation that allowed us to extract just the pixels that belonged to one rice grain here. I think it was rice grain 12. And we had another case where we applied that and extracted rice grain 25, which I think was somewhere around here. Yeah. So in both of these cases, when we did that Boolean operation, so it was the label being equal to 12 or the label being equal to 25. What we end up with is exactly a binary image, which is the Boolean, the pixels in the array that satisfy that Boolean condition. And so this, we could apply this calculation to, and we simply end up with the number of pixels in this region. So M00 tells us the number of pixels as an area within this region. And so we could see how many pixels would be in this region from M00, and also how many pixels would be in this region. Going back to this, we can also, when we do these calculations here, we're effectively getting a measure of the sum of all the row coordinates and the sum of all the column coordinates from M10 and M01. And therefore that's related to the, it's basically giving us a measure that's related to where this region occurs in this image and where this region occurs in this image, if we applied it to this as well. So, and indeed you can from M10 and M00, you can find the centroid for a region in terms of its row coordinates and its column coordinates by this calculation for the row coordinates, so M10 over M00, and for the column coordinates, M01 over M00. Now, some of you may have spotted also that these calculations here we've met before. So if we go back to chapter 1, we see that actually here you can see in calculating A0, we simply have this expression here. This is the sum of all the pixel intensities, and so if this is a binary region, then A0 is equal to effectively the calculation for M00. Similarly, we see that the numerator of this term here corresponds to M10, and the numerator of this term corresponds to M01. So these calculations can be also used. So the moments, if you like, can also be used for estimating in a grayscale image, because this expression actually also applies if f is non-binary. And so you can also use these expressions to calculate or to do the fit of the bilinear image model. Okay, so maybe we do a little calculation just to show how those centroids. Well, I'll do that as a separate video just to save time. But if you want to know how we run through those calculations, then to get m bar and n bar, and see how intuitive it is, there's another point that I'd like to make about this. So I will do that as a separate video. Okay, so given that we've defined the first order moments, we can now move on to define the central moments. And the central moments of a binary region are defined using a quite similar equation. The only difference is that first, what we do is we calculate our centroid coordinates. And just to remind you that the expression we had before for the moment calculation was m raised to the power of p and n raised to the power of q times fmn, and then summed over the region. For the central moments, what we do is we raise m minus m bar. So we basically do this calculation. We subtract the centroid, the row coordinate centroid, from all the m coordinates before we raise that coordinate to the power of p. And we do the same thing for the column coordinates. Okay, so these are now deviations, if you like, from the centroid, raised to the power of p and q respectively. And so these give us the second order central moments. And the second order central moments, these are the definition of the central moments. For the second order central moments, which are the most useful things, the things you'll most commonly come across, you have mu20, mu02, and mu11 all being the second order central moments. And so in all cases, again, p plus q sum to 2. So here you've got p is 2, q is 0, p is 0, q is 2, p is 1, q is 1. And so these are the calculations that all correspond to the second order central moments. So what do these tell you about? So so the second order central moments, I'm not sure I've got that here. Okay, so I haven't got it here. But what these tell you about, and you can find a little bit about how, what information these things give you. But what they tell you about is the degree of elongation of a region. So actually, I think I'll swap to my board scene to explain this a bit better. So the second order central moments. So let's just write about these now. Okay, so here's my pen. Good. Okay, so whoops. Let's use that. Right. So second order. So second order central moments, and in particular we must emphasize that these are the second order central moments, not first order, and they have to be central moments. What these tell us about, so let's say we have a region that looks like this. Okay. The second order central moments give us a measure of the elongation of the region, and it does so in two orthogonal directions. So how do we get that information? So first of all, the information is kind of encoded in the second order central moments. So remember, our second order central moments, we will have 3 second order central moments. Which are going to be mu 20, mu 02, excuse me, and mu 11. So if we take these 3 second order central moments, we can form what's called the central order moment matrix. And all this is a little 2 by 2 matrix which contains these elements. But you might think, okay, we've got 3 elements here. How do we make a 2 by 2 matrix with these 3 elements? So it looks a bit like this, or it looks like this. So mu2, 0 goes there. Here we have mu1, 1. Here we have mu1, 1 again. And here we have mu0, 2. And because we have mu1, 1 repeated here and here, we've kind of reduced let's say we have a special case of a 2 by 2 matrix. And so it turns out a consequence of this structure is that we have 2 orthogonal eigenvectors associated with this matrix. And the eigenvalues of this matrix tell us about the degree of elongation along. So the principal eigenvalue tells us about the length of this ellipse that we can sort of, or the length of an ellipse that best fits our elongated shape. And the second eigenvalue tells us about the width of the ellipse that describes our binary shape. The ratio between lambda 1 and lambda 2, assuming lambda 1 is our principal eigenvalue, so if lambda 1 is greater than lambda 2, then the ratio lambda 1 over lambda 2 tells us about how elongated our region is. In particular, if this region were sort of more circular, then lambda 1 would be approximately equal to lambda 2, so you don't get much difference. But in practice, you will have some sort of measurement difference, some sort of noise in there. So usually there'll be an eigenvalue that tends to be bigger. The eigenvectors associated with lambda 1 will tell us about the direction of elongation as well, and of principal elongation, and then lambda 2, the eigenvector associated with that, will be orthogonal to the principal eigenvector. And again, the 2 eigenvectors for this array will be orthogonal because of the limited structure of this array. That is, the mu1, 1 is sort of repeated here. So you have you've sort of limited the degrees of freedom of this matrix in terms of the structure it describes in 2-dimensional space. So that moment matrix is nifty because, as you see, the definition only comes from the moments, and it can also be extended to 3 dimensions. So if you've got some kind of 3-dimensional structure and you want to characterize that structure, you can, and it's represented by as a sort of a binary region in a 3-dimensional array, then you can extend your moment matrix to include moments that go, again, second order moments, but those that go into the 3rd dimension, and then you're able to use the eigenvalues and eigenvectors of that 3 by 3 matrix in order to characterize your 3-dimensional structure. So that's one of the nice attractive things about the second order moment matrix. Okay, let's now then move on to looking at just wrapping up this chapter. So as I've mentioned before, you can also, in all the definitions of here, we've taken f to be a binary, so to have values of 0 or 1, but you can also apply this to the case that f has non-binary values, so you have floating point values or whatever, and you can also construct gray level moments too. So just bear that in mind. Okay, we're just going to talk now about a couple of things, just wrap up quickly. So first of all, there's a technique called the medial axis, and I'll just show you first what a medial axis looks like. So this is the medial axis. That is a way of simplifying the structure a binary image structure to find its skeleton. So we're going to look at some tools to do that when we get to morphology, but one of the nice techniques that one can use to do that in a binary image is based on something known as the distance transform. So the distance transform, well, there are lots of nifty algorithms you can use to work out a distance transform. But effectively in a distance transform, what you do is you replace your binary image with another image that tells you how far each binary pixel is from the boundary. And because you have different notions of how to measure distance in a digital image, so you can use city block distance, you can use chessboard distance, you can use Euclidean distance, then there are different types of distance metrics that one can construct. So this is a simple algorithm to construct distance, a sort of an approximate distance transform using a chessboard distance, if I'm not mistaken. And you may want to see if you can work through this and figure out how this comes about. I think I've got a demonstration of how this works recorded somewhere on Blackboard as a series of different steps. But if not, I'll post it up. But what I wanted to show you as well is, and hopefully I've got this somewhere on one of my open windows. It doesn't seem to be here, so let's just have a look at it, have a look for it. Distance transform Python. So there is a SciPy documentation on this. It's in one of the Python packages. Actually, this is the old one, so we want to go to the latest one. And the distance transform is somewhere in here. Now let me see if I can know. It's an ND image. So this is for n-dimensional images, and it's not. It should have been in measurements, but it's actually in morphology. So it's down here. So there you go, distance transform. And there are some demonstrations of what a distance transform looks like. So that's the sort of thing that a distance transform looks like if you are using a chessboard metric. And if you use a different metric, then, that's the taxicab metric. And then that's the chessboard metric. So you get slightly different results depending on which algorithm you use. The Euclidean one is a bit slower. The one I've shown you here is, I think, chessboard. It works reasonably well, and I think that's the one that I used to create the skeleton I did here. But once to create the skeleton, what you first do is you apply a distance transform. So create a distance transform where every pixel tells you how far it is from the nearest boundary point, and then from that you can then compute the skeleton or the medial axis by finding the pixels that represent ridges in the distance transform. And so what we're doing here is we're collecting the pixels such that the pixel is not zero. So in other words, it's not outside in the exterior region of the binary region. It's actually inside the binary region. And secondly, it's such that in the distance transform result, the value of the pixel at mn is greater than or equal to the value of its four connected neighbors. So that's the approach that I use to compute this distance transform here. This medial axis here of that. So from here into distance transform, and then from that into medial axis. So that's a nifty trick to bear in mind. So the skeleton of the region is useful if you want to, for example, describe blood vessels. You have an image of blood vessels, but you really want to focus on geometry and connectivity. That's where you would use the distance transform. The medial axis. So the medial axis basically thins the vessel out, and you can just focus on connectivity, for example. Okay, so just to summarize what we've done so far. So we've looked at binary images, and we've let me just drop back to the lectures here. So we've looked at We've looked at binary images where the number of intensity levels is restricted to 2. And the reason for doing that is that it allows us to focus on connectivity and structural form in 2 dimensions, and to introduce ways of representing binary image regions. And so even in the most, even within most deep learning systems, deep learning networks, people talk about the networks all the time and how they're designed, etc. But actually very often the output of a network is some kind of probability that tells you about, that gives you a label which you then threshold, and that thresholded region often will be subjected to some further processing, and that's where the binary image processing might come in. But you can use binary image processing to do a lot of useful things, and in particular connected components labeling assigns, for example, unique label to each distinct object of interest in a scene. Once you've done that, you can then go in and grab the pixels that belong to individual regions and do something useful with that, summarize those regions in some way. So that's kind of what we've been looking at. So the techniques I've described in this chapter do have their place, but they are almost never complete solutions to the task of image analysis or computer vision. You shouldn't ignore them because they can be really useful at times, but don't assume that you can do everything. I mean, you're going to be doing a practical on counting objects in a scene and doing thresholding and characterizing regions using the techniques we've discussed in this chapter in your practical. But it's easy to get carried away. So those techniques are there to give you some insight and some very simple tools that you can use to tackle problems quickly, but they are almost never complete solutions to the problem of interpreting or analyzing the data that's present within a scene. Nevertheless, they can be useful, particularly if you need to get some results quickly. Then you can use thresholding and connected components, and then characterize regions using the measures we've talked about here. So one of the places that these techniques are still widely used, as I mentioned before, is in industrial vision or machine vision. That's where you've got a camera that's sitting looking at a conveyor belt or looking at some sort of bench, and you want to analyze. So you have very well controlled lighting, you have very well controlled camera position, and the objects are limited in number and positioned kind of in a plane. So in those settings, you can use these techniques. They really work pretty well, and they can be super fast. So in factory settings, if you need to do very quick sorting, you use these techniques. When you're dealing, however, with rather messy medical images, or images of the real world taken, let's say, with a mobile phone camera, which is taken out in the wild, or as you walk down the street, then these techniques will have very limited success, unless they are combined with more sophisticated approaches, such as those based on machine learning.